The AP1000 is a new Gen 3 Plus pressurized water reactor, or PWR. It is a nuclear reactor made by company Westinghouse. A PWR is the most common type of reactor, with the other type being the boiling water reactor, or BWR. The AP1000 and the AP600 are the two newest reactors to be approved by the NRC. These new Gen 3 Plus reactors are much more standardized, have improved safety features, and more importantly, are cheaper to construct. Standardization allows licensing and inspection processes to be easier and faster. Plants will also have identical types of equipment, control rooms, operating rules, training, and safety measures. Companies with similar plants can compare operation procedures and improve upon them as a whole, instead of allowing each to evolve independently. The AP1000 has focused on simplification of systems in order to improve safety and reduce cost. The nuclear island basemat design, which is what is currently being used at Plant Vogtle, allows for cheaper and shorter build times. Modular design allows for the plant to be built off-site and just dropped into place, rather than having to build on-site. The improved safety features include more passive features that are less vulnerable to failure because they do not rely on electrical, mechanical, or human actions to operate. Some of the advancements of passive safety features have been made after Fukushima and 3 Mile Island have shown the dangers of relying on off-site power.
One of the first lines of defense from accident is a level of redundancy to the processes in order to absolutely minimize the chance of an unplanned event. Though some features are not rated as being safety related, much of what could go wrong is effectively stopped at this stage. By integrating these systems into the processes of the reactor, a greater efficiency is achieved by providing shorter downtime from inspections. Some of the features include chemical and volume control systems, a residual heat removal system which is constantly working to maintain temperatures within the reactor, and an auxiliary feed water system for use during startup. Though none of these systems are unique to the AP1000 reactor, by maintaining a reliant system of checks and balances, the majority of dangers are caught too early on to become a problem. Now, for the passive safety-related systems. The first is the passive core cooling system. Now, this utilizes a passive convection as well as a pressurizer in order to maintain pressure in the lines in case of a break. After the pressure has exhausted its supply, water and then steam are used to maintain pressure. It has an 8 million pound water tank that gravity feeds the entire system. Here is a graphic that will show in a little bit more detail the processes of the passive cooling system. The next is the containment isolation. It's a simple enough idea that fission products wouldn't be able to reach fluid lines running through the reactor. In the case of an incident, through simple isolation of the lines, they can prevent contamination throughout the rest of the system. The next feature is the passive containment cooling system. Outside air and water are used to cool the top of the steel containment dome. Through the evaporation of the gravity-fed cooling lines and the effects of convection within the reactor containment, the core would remain cool enough as long as the cool tanks remain supplied. Their capacity is enough to last 72 hours, and connections are available for alternate sources as well. Main control room emergency habitability. The control room may be isolated. In the case of high airborne radiation levels, it is equipped with an air supply to accommodate 11 people for 72 hours. So even if something goes wrong, the control room will be able to remain isolated and safe for human habitation for up to 72 hours after the event.
When it comes to nuclear reactors, capital investment is the name of the game. Companies have to convince people to put down large sums of money initially rather than over time, therefore making construction of a reactor a huge investment. Westinghouse is staying competitive with the improved AP600, named the AP1000. Westinghouse believed that the best way to reduce costs was to reduce the volume of the entire plant. One might think that this leaves out safety, but the changes have actually made the power plant much more safer. The engineers ran plenty of computer simulations, such as the RELAB 5 computer code developed at the Idaho National Laboratory, and is used to run core modeling and coolant simulators to find the most cost-effective construction. Also used was the ASTEC, known as the Accident Scores Term Evaluation Code, to analyze severe accidents and reactor safety. During this run, there was a faulty test that needed more work, which was the odd behavior of the vessel head wall temperatures and critical heat exchange. Yet most of the final tests proved exemplary, such as the simulation of molten core, where the temperatures were not melt the steel. These improvements have brought about modular construction, which can be seen driving past Plant Vogtle. Large parts, such as reactor vessels or part of the containment vessels, are prefabricated elsewhere and brought to the plant to be placed together like gigantic Legos. The AP1000 design was approved in late 2005 by the Nuclear Regulatory Commission, and it could not have been at a better time. Southern Company was planning on building additional reactors for Vogtle, but more importantly, China was and is still hungry for more energy. Some higher estimates show that they have plans on building 29 reactors to increase its share of reactors with the world from 3% to 20% by 2035. And there's a huge chance several of these will be AP1000s. The future of the AP1000 is just beginning, as the first reactor is going online this year at the Sanmen Nuclear Power Plant in China. This will be the test to see if everything goes well for other power plants that also want to expand their program with AP1000s. While this might not seem like a big deal, this is the first nuclear power plant to be completed after Fukushima and will bring plenty of media attention. A price of $5.88 billion was paid for the first two reactors purchased from Westinghouse by Sanmen. With competition in the Far